I'm going to talk about a particular kind of standing wave that has boundary conditions on it because it's taking place on a finite length object. We're going to talk about the standing wave that occurs on a vibrating string like a guitar or a piano or a harp. And because the string is only a certain length, this poses certain conditions on what kind of standing waves can take place. If we imagine a guitar string, it's clamped on both ends, and so even if it's going through a standing wave motion, in other words, it's oscillating up and down, there are certain things that we know have to be true. We expect to have nodes at the end of the string because no oscillation is allowed at the ends. The clamping makes for no motion of the string there possible, although it can have very large motions out in the middle. So if we were to write the functional form of a standing wave, remember it's y of x and t is 2a sine kx times cosine omega t. Well, when I plug in x equals 0 for the left end of this string, then I expect to have this whole function be 0 because I'm at a node. That works out to be true automatically because when I plug in 0 inside the argument of the sign, well, that's just 0, so that's no big deal. But it's also got to be a node at the other end of the string, and so when I plug in x equals L, I have to have 2a sine kl times cosine omega t equals 0. That means that for any time t I pick, this thing has to be 0, which means that the argument of the sine function needs to be a multiple of 2 pi. When that's true, the sine is always 0, and I will have a node as I desired. If I remember what the k function is, or the k wave number is, k is 2 pi over lambda. And that means I can rewrite this expression kl as a multiple of pi to become lambda is equal to 2l over n, where n is an integer 1, 2, 3, 4, or so on. Those are going to be wavelengths that are allowed to have standing waves on a string. Any other wavelength won't be possible because it won't be able to create a node at the ends of the string as I require. There are variations on this. We can try to imagine what if we put our finger down in the middle of the string, just like we do when we play the guitar. Well, this creates something similar, except we have to put an additional node. We have to have a node at L over 2. So in addition to saying y of 0 is got to be 0, we have to have y of L over 2 is 0, and y of L is equal to 0. This requires that kl over 2 has to equal a multiple of pi, or written in terms of the wave number 2 pi over lambda, I get lambda is L over n. That's just a slight variation, but all we're doing is forcing this string to have nodes at required places. But the more general form for a free oscillating string is 2L over n for the allowed wavelengths. Now, how does that relate to pitch? Well, pitch or frequency and wavelength are all related through the speed of the wave. Now, something we haven't talked about, but you need to know, is that the speed of a wave on a string depends on how much tension there is in the string and how thick the string is. Its linear mass density, which is measured in kilograms per meter. It's just how much the string weighs. The velocity of a wave along a string depends on the square root of the tension over the mass density. So the more the tension, then the more the velocity of the string. The reason we have pegs on the end of a guitar neck, for example, is so you can adjust the tension and you can change that velocity by a little bit. It's also true, if you look at a lot of stringed instruments, that the strings are not all the same thickness. In this guitar, for example, the strings on the left are thicker and heavier per unit length than the strings on the right. And the same would be true of a harp or a piano or any other stringed instrument. One of the ways that the difference in velocities is achieved is by varying the mass density, mu. If you remember, the frequency and the wave speed and the wavelength are all related through the equation F equals V over lambda, or V equals F lambda. So if we would like to know the frequency of a pitch created by a vibrating guitar string, we should take V divided by lambda, and lambda is 2L over n, so we can plug that in, and V is square root of tension over mu, so we can plug that in. That means we have a way of predicting what frequencies will come off of a stringed instrument, given the tension, given the mu, and given the length of the string. Notice that only certain frequencies are going to be possible on a string of certain length, and that's why either you're playing a harp and you have different strings all along, or piano where the different strings have different lengths, or you're playing a guitar and you intentionally change the length by putting your fingers down and clamping and creating a node. In terms of frequencies, you can create lots of different frequencies by creating different so-called harmonics or different integer ends on the same length string, but this is harder to do. And this just shows us the scale as well as some different frequencies that can be created for a certain length string and a certain number, the certain resonance or n number for each of the resonances along the string.